Yes, sir.
Yes, sir.
Discussed the Denavit-Hartenberg convention, and this convention was meant to have a clear method to fix frames on links. Now, we had, if we are to summarize this method, the first thing that we did was we created, or we rather identified the joint axis. So we identified the Z I minus 1 axis. Then we identified the Zi axis, Zi plus 1 axis, and so on. All the the Z axis. And these were the axes about which the relative motion between these two links were taking place. Here we assume that only one variable, joint variable, is changing. Now in this, if we are to consider a revolute joint between link I minus 2 and link I minus 1, we get this common joint axis Zi minus 1. This is the axis about which the relative motion between link I minus 2 and link I minus 1 takes place. In the same way, we also have this joint axis Zi. It is the axis about which the relative motion between the link I minus 1 and link I. Link I is not shown completely here. It takes place between this. Then, having identified the Z axis, we proceeded to identify the link lengths. So the link lengths were determined by the shortest distance between the joint axis. Now, if we have skew axis, we know that we have only one common perpendicular. If the axis Zi minus 1 and Zi are skew, it's possible to have only one perpendicular to them. That would be the shortest length. That would provide us with the shortest length. Naturally, it would be perpendicular. It would be perpendicular to the axis Zi minus 1 as well as perpendicular to the axis Zi. In case, I think, yeah, in case we have a prismatic joint, in that case, this link would just translate with respect to its previous link. Okay. Same thing. In case we had the joint here as a prismatic joint, then the ith link would just translate with respect to this. When we say translate, it means there is no relative change of orientation between these two links. Okay. So we constructed the common perpendicular and we determined its length and we called it the link length. In fact, it gave us also the direction of the axis, x axis, corresponding to link I minus 1. So that was shown here as xi minus 1. And that axis is actually starting from Zi minus 1 and proceeding towards Zi. In case the axis Zi minus 1 and Zi are not skew, that means if they are parallel, in that case we will have a perpendicular, but we would be having infinite number of perpendiculars. But all these perpendiculars would have, the common perpendiculars would have the same length. Okay, so we have taken a very general case where it would be askew. The axis Zi minus 1 and Zi would be skew. So having identified the link length, the next thing we proceeded with was the link twist. For that, the link twist offered us the relative orientation between these two joint axes. So we kept our thumb oriented along this xi minus 1, okay, and turned our fingers from zi minus 1 towards a line perpendicular to zi. That line perpendicular to zi was brought here. Okay. Not perpendicular, I mean parallel to zi. It was parallel to zi, so it was brought here. Okay. It's parallel to zi. So the angle that was so obtained was called as the link twist, alpha I minus 1. That's how it was designated. Then we proceeded to determine the joint variables. So corresponding to the links, we have only two parameters. One is the link length and the link twist. These are enough to give us the relative position and orientation between these two axes, joint axes. Coming to the joint variables, let us focus on the joint I. And at the joint I, we have yesterday this figure appeared a bit difficult, I thought, because the angle theta I was difficult to imagine. So I made a slight modification to it. Instead of showing it downwards like this, I have shown it upwards so that you can see a positive theta I. And so I've already prepared that figure. I'll just show it to you here. Yes. So the rest of the figure being the same, it's just that we have changed this angle. I have shifted the x-axis, that is the axis that is connecting the I plus 1th joint axis to the zi. Okay. So here you have zi plus 1 and here you have zi. And this is the axis which is perpendicular to both of them. So we have here zi and it is perpendicular to xi, and it is shown here using this symbol. If we draw a line parallel to xi at this location, okay, we will be able to obtain the joint offset. So the joint offset is the distance that is measured along the zi axis. You can keep your thumb oriented along the positive direction of the zi axis and measure the distance from where xi minus 1 intersects the zi axis to where the xi intersects the zi axis. So this distance is di. It is called as the joint offset corresponding to the ith axis. And finally, we have the joint angle corresponding to the ith axis. That is the keeping your thumb oriented along zi. You move your fingers from xi minus 1 towards xi, or a line parallel to xi. So this is going to be the angle theta I. And I think now this figure is more clear than the one we had previously. So let's stick to this. And as a summary, these two link parameters corresponding to link I minus 1 here, and the two joint variables corresponding to the joint zi here, they are mentioned. Now, the next thing is, you see here we have got two frames fixed. The frame I minus 1 is fixed on the link I minus 1. And the frame I is fixed on the link I. or an extension of it. You see, it's not necessary that these frames should be fixed on the physical link itself. They could be fixed on an extension of that link as well. And that's the reason why deliberately I have not taken this common perpendicular over here. Okay, I wanted you to come to a situation. Physically, the link I seems to be here, but the axis xi appears to be here. That is because the common perpendicular is, I wanted to show that it's not necessary that it should be physically present on the link I plus 1. It could be on an extension of that. So we have these two distinct frames, frame I minus 1 and frame I. I hope all of you can hear me.
Yes, sir.
Yes, sir.
Yes, sir.
We'll continue.
Yes, sir.
Okay, fine. So now our next job is to work out a transformation, a homogeneous transform, which will relate the positions expressed, observed and expressed in the frame I to the positions observed, to those observed and expressed in the frame I minus 1. So if in case we have a point P here, okay, if we have a point, let's say a point P, and we know that the location of this point P as observed by the observer in the frame I would be like this. He would see it like this because he's sitting here, and this would be the position vector. So this is the position vector of the point P as observed by the observer here in the frame I. But the observer in the frame I minus 1 is going to look at this same point. Okay, but how is he going to see it? He is going to see it as this vector. Right? So he sees it as this vector, and he will express it in terms of his coordinates. So we have two distinct vectors. They are different. This is the position of the same point P, but now it is viewed by the observer here. The observer here in frame I minus 1. And he or she observes it as this vector. And when is going to express it in terms of the components in his or her reference frame. Okay. So we have these two distinct position vectors. How are they going to be related to each other? So for this, we will have to work out the homogeneous transformation between the two. We know that these positions can be related to each other through the homogeneous transformation. So we could have a position of the point P as seen by the observer in frame I minus 1 and expressed in his frame itself. And we could augment this vector with the 1. So it becomes a 4 by 4, 4 by 1. Okay. And this is equal to This is related to the position vector of the point, same point, but seen from the frame I, expressed also in terms of the coordinates of the frame I. That means something which is done by this observer. And here also we will augment it with 1. So this also becomes a 4 by 1 vector. And we know that the relationship between these two is given by the homogeneous transform, that is the T matrix from I to I minus 1. I minus 1. I corresponding to this, I minus 1 corresponding to this. So this is our 4 by 4 T matrix. This is a 4 by 1. This is a 4 by 1. And this is 4 by 4. We know the structure of this matrix. Now our job is to determine this matrix. And you see, we have used the suffix I, and this is general. We could change I from 1, 2, 3, 4 and all. And thus we can get the transformation of the ith frame with respect to its previous frame. So let us begin with this task. I'll take a fresh slide, make a copy of this. Yeah. So here, first of all, we already have the frame I shown here. Okay. And as we had discussed yesterday, we have only represented two of the axes, xi and zi, not the axis yi. And the reason for that is because we don't want the figure to be too cluttered. We know that if we turn from xi towards zi, keeping our right hand, using our right hand, the thumb will indicate the direction of the y-axis. So there is no need of representing graphically the y-axis. So now let us start with the process of obtaining this transformation. Let us first construct a frame which is parallel to the frame I, but shifted down, over here. So we will position this frame here. We'll keep it here. So this axis is corresponding to Zi. This axis is coinciding with. So this is our first. Let's call this frame as frame H. So we will take this frame as frame H. So this becomes ZH, and this becomes XH. Okay, this becomes the origin of the frame H. Now our first job is we will write down what is the position of the same point as observed in this frame H. How does it look? You see, the frame I is just translated with respect to the frame H. If the observer is standing here in the frame H, he will see that frame I is just translated. Its axes are parallel, but it is shifted over here. So there's a movement along the z axis, and it is by an amount of di. So the first thing is that the observer, uh, the t, let's say, shall we construct this? Yeah, I think we'll write it here. So we'll construct this transformation matrix, which is relating the frame I to frame H. So we have, it's a pure translation. So there is a unit matrix 1, 0, 0, 0, 0, 1, 0, 0, and this is 0, 0, 1, 0, and this is pure translation. The origin of the frame I as observed by the observer in frame H is di units along the z axis. So this will be along the z axis. So the z component is going to be di, and this is going to be 0. This is going to be 0. Okay, and here we have 1. So this is the transformation matrix, which is going to link, which is going to give us the relationship between I and frame H. Okay. So when you operate on the vector Rp with respect to I expressed in I augmented with 1, when you operate on this 4 by 1, okay, you will get the position of the vector in frame H, observed and expressed in frame H. In fact, I shouldn't be writing even this over here. It will also be H, because we are doing it with respect to the origin of the frame H. Oh, I'm sorry. This is okay. This is okay. It's a transformation from I to H. Okay. The next is we will determine what is the transformation between this purple frame and between another frame which is over here, which is parallel to this frame. So we will take another color. Let's say we could take the blue color, or maybe the red color. Let's take. So here, let's take some other color. Let's take green color. So here, we keep this axis as a pure rotation. We have this green axis here. and this is, let us say, frame. Let's say this axis is ZK. This also we will say is XK. This axis is XK. Okay. Naturally, the origin is over here, and if you see the observer over here in green, the observer here in green, how the axis, how does he see the reference frame H? The Z axis are common, but the X axis of frame H is rotated with respect to the X axis of frame K by an angle of theta I. And we know what this transformation is. So this transformation we can write as transformation from H to K. It's also a 4 by 4 matrix, but it's one of pure rotation, and because it's pure rotation, there is, the origins are the same. You see, the origins are coinciding. So here we will have 0, 0, 0, 1, because the origin of frame H is coinciding with the origin of frame K. So 0, 0, 0, 1. What about the orientation? We know that it is a pure rotation about the Z axis. So the Z axis will remain unchanged, that is 0, 0, 1. Here there will be a 0. And we know what the rotation about Z axis, what is the transformation. So here this is cos theta I. Okay, cos theta I. Here it is sine theta I. This is going to be 0. And this is also going to be 0. Here we will have minus
Sin theta I. Cos theta I.
This is going to be cos theta I, and this is going to be 0. And here also we have 0. So this is the transformation, this is the homogeneous transform that will take us from the position of the same point P, okay, but as observed and expressed in the frame K. Okay, so let's now proceed further. Now we will assume another frame. Let us take this frame in red this time. Not red. We'll take it in some other color. What is available? Could take it in orange color. Okay. So now, having obtained the coordinate, the position vector in the frame K, we'll just translate this and bring it here. So we'll have the frame which is parallel to K, like this. So this is corresponding to x, let us say this is xl and this is zl. Okay. So what is a transformation, homogeneous transformation from K to L? The observer here in the frame L, he will see that this frame K, the green frame, is just pure translated as if it is shifted along the x-axis. And you also know how much it is shifted. It is shifted along the x-axis by the length of ai minus 1. So accordingly, here, can you tell me what will come here? The origin frame K with respect to the frame L. What is the location of
What is the
that?
location of that?
AI minus 1.
AI minus 1.
So this is a I minus 1. This will be 0 and this will be 0. This will be 1. What about this? Here we'll have a unit matrix. Agreed? So 0, 0, 1, 0, 0, 1, 0, 0, and 1, 0, 0. So with this transformation, the vector P will be observed and expressed in the frame L. And finally, we know the transformation between the frame L and the frame I minus 1. And you can see that the frame, when seen from frame I minus 1, the frame L appears as if it is rotated about the x-axis of I minus 1 by an angle of alpha I minus 1. Okay. So let us take this finally. We'll take this in. So I'm going to write it as the transformation from L to I minus 1. Okay. This transformation matrix given by T, it is just a pure rotation. It's just a pure rotation. The origins are coinciding, and so this part will be 0, 0, 0, 0, 1. What about this here? It is rotation about the x-axis. So what will change? X-axis will remain unchanged. 1, 0, 0, and 0. What will happen here?
0.
Here also it will be 0, and here also you will have 0. Here you will have
Cos theta.
theta or what?
Cos
Cos
cos alpha minus 1. Cos
Alpha I minus.
I minus 1.
I'm writing it as C alpha I minus 1. Okay. Here we will have sine alpha I minus 1. And here we will have 0. Here we'll have minus sine alpha I minus 1. Here we'll have cos alpha I minus 1, and here 0. Now I want all of you to multiply these matrices in this order. Okay. What will this multiplication give us? It will give us, if you just multiply these transformation matrices, what are we going to get? We will get, can you tell me?
Position, sir.
Position
No,
of P with
position we
respect
will
to
get.
x.
We will get a position when we multiply it with this. Okay. So, okay. If position is what you're talking of, then we can write it as position of the point P as observed and expressed in the frame I. Okay. This is being operated on by a transformation matrix. This transformation matrix which we have mentioned from I minus from I to I minus 1. Okay. Now this part is already here. This part and this. So this is position of point P as observed and expressed in frame I minus 1. Okay. So what is this T matrix? It is just the product of these four matrices. I hope you can see that. So
Yes, sir.
this part is already here. This is the position which we are going to get. Position of the point P as observed and expressed in the frame I minus 1. Okay. And this transformation is going to give us, if we are to work out this transformation, which is the product of these four matrices in this order, then we will get the transformation matrix, a single transformation matrix Ti to I minus 1. Now it's a square matrix, 4 by 4, 4 by 4, 4 by 4, 4 by 4. So this T matrix is a square matrix naturally. Okay. I want all of you to do the multiplication now, and or maybe you can do it as a part of your homework, and verify for yourself what is the expression that you are getting. Okay, so you should get the expression, you should get this expression here. So you should get this expression. Okay, so this transformation from I to I minus 1, you should get this expression. So I want all of you to confirm whether you are getting that expression or not. So please do it as a part of your homework. Um, okay, please check. This is your homework. It would take a few minutes only to do it. And I want all of you to confirm whether you are getting this expression or not. Okay, you should get it. When you multiply these four matrices, you should get this T from I to I minus 1. Okay. Um, so we have still around 5 minutes left. I plan to take an example. Just we'll discuss the example today, and we'll do that example completely, possibly in the next class. I have here a manipulator which used to be very popular. It's a schematic of the PUMA manipulator arm. Okay. And what we are doing now is just an example. So it's just an example uh, on how to fix the um, frames on the links using the Denavit Hartenberg convention. I've also reproduced the transformation matrix just for reference. Now, let us see here. This particular manipulator arm, here it's not in its full configuration. Here we just have what we would say this is a fixed base, okay, and about this fixed base we have the rotation of this part here, which is the waist, okay, the waist. So it would turn about its waist, okay, about this axis. uh, so this is the first um, degree of freedom. The second is the shoulder. So here motion is about this axis, and this has um, motion relative about this axis. Okay, so you have this link and you have this motion. And the third is you have the elbow here. Okay, the elbow, and here also it's a revolute joint. So all these three joints are revolute. The first two axes are mutually perpendicular to each other, but the third one is parallel to the previous one. You could have a tool fixed over here. In fact, you could have 3 more degrees of freedom depending upon what kind of attachments you have here. They have not been shown in this configuration. This is just because it's a simple example to explain to you on an industrial manipulator. This used to be a very popular industrial manipulator um, in the early days of robotics, and it is called the PUMA Robo Manipulator Arm. It was a product of Unimation Incorporated, Unimation Inc., and it was founded by Joseph Engelberger, the same person about whom we had discussed in our introductory lectures on robotics. So the process that we will fix up a frame on each of these links. Okay, so here we have the frame 0, which has been written as frame XS, ZS, and YS. Okay, but we could take it also as X naught, Y naught, Z naught, Y naught, and Z naught. And here the other links, we have yet to fix up the frames, and we still have to determine what would be the Z axis and what would be the X axis and how they would be moving. So once we have that, we will identify the link parameters and the joint variables, and we'll arrange them in rows. And you will see that this transformation that we have here, so it is just involving these four quantities, ai minus 1, alpha I minus 1, di and theta I. You have nothing else in this. Okay, you have all these four quantities here in this transformation, and we'll make use of that. We'll put all these four quantities in a single row, and we will construct, in this example, we'll construct a table of parameters and joint variables. So that will be our next job. And then from those parameters, from those rows, each row will give us a separate T matrix, transformation matrix. So this is what we will do, and we will take up this problem in our next lecture. If you have any difficulty or doubt, please don't hesitate to ask me now.
Sir,
Yes.
sir, this convention is used in any other type of joint?
This
It's like parallel joint.
Denavit-Hartenberg convention is very popular for in robotics and mechanisms. Okay.
Yes.
We can also use the same convention irrespective of whether it's a prismatic or a revolute joint. And you see the other joints like a spherical joint, for example, it
Ball
can
and
be realized using a combination of more than one revolute joints. Okay,
yes.
so you should know this fundamental transformation, and then you can extend the other joints. Okay.
Yes, sir.
Yeah. Any other query? If you don't have any query, then we can conclude here for today. Okay.
So this PUMA robot manipulator is used in industries for this for the
It
industrial
used to be,
purposes we use.
it used to be used in the good old days. Now, old days means a couple of decades ago, maybe till a couple of decades ago. But today you don't see the PUMA industrial robo. It used to be used for welding, for assembly, for spray painting, etc. In the automobile sector, especially. So it has been a very popular robo during its time. It was the initial stage, and it is also visible in many of the educational institutions in India. I am not sure whether they still use it in their respective labs, but you will certainly find it in some corner in especially in the IITs and other institutions of repute. Yeah. Any other query?
Sir,
Yes.
sir, sir, क्या बोलते हैं? क्या each joint having a single degree of freedom, it is necessary?
It is not necessary, but it simplifies. It helps us to obtain the transformations in a simple manner. You
Yes.
can have more than one degree of freedom. Say, for example, a spherical joint. Okay,
Yes.
it has more than one degrees of freedom, right?
Yes.
So it can be realized using a combination of two revolute joints. Do you agree?
Yes, sir.
Yeah. So, in fact, you can use three revolute joints, all co-located, origins of co-located at the same point. So, you can go step by step, just like how we did. We produced these four reference frames, and then we did a transformation one to the other to the other. In the same way, you can also do it for a spherical joint. Okay, it can be done. Any other query? Okay, then since we don't have any more questions, we'll summarize here. We'll conclude here for today. Okay. Thank you very much. Have a good day.